Okay, everybody can see me, hear me, see the screen, all that jazz.
Yeah.
All right, so homework for today was to, so last class we wrote decimal to base, right? We wrote several iterations of, I think we originally wrote decimal to binary, then solved the decimal to octal is the same thing, then we wrote decimal to decimal because that's funny. Then we wrote decimal to hex, and we saw how we had to do a little bit extra there to do the mapping between the digits and the hextets, right? I think it's the A through F. So today we're writing, well, for today we were writing base to decimal. So our second pattern going back the other direction. This guy should take a string representation of a number as well as the radix, which is the base. And it converts that back to decimal. So we have to pass in a string as well as what base that string is in, because we do need to tell ourselves what base it's in, right? Because I can tell you if I put the number 127 in there, that's a legal octal number, right? That's a legal base 9 number, 10, 11, 12, 13, 14, blah, 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 blah. Okay, it's not a legal base 2 number because it has values greater, not 0 or 1, right? So a base n number contains legal values of 0 to n minus 1. Legal, I want to say digits, but it's only digits if it's technically base 10, but I think you get what I'm saying. Okay, so we do need to take in what the base is. So the idea is if I took in BAD and 16, it would give me 2989. All right, so let's start off by writing this for just base 2, and then we'll modify it. So kind of start with a simpler case and then look at the kind of the special mapping after that. All right. So what I'm going to do here is I'm going to actually get rid of all that stuff. We'll just start with a clean slate. So remember last time we talked about this idea of all programs begin and end with main. So we actually created for us a situation where we have a main method we've artificially created, and that's the guy that automatically gets called when our program launches. And he's like kind of the quarterback for our program. He drives the execution of our quarterback. He says what to call next, how the flow of logic happens. All right, so we're going to go ahead and define a function, and we're going to call this guy binary to decimal. Okay, and he's going to take in a binary number. We'll call this guy a bin string. Now, I don't actually have to take in the base here because we know since it's binary, it'll be base 2. So we'll just leave it blank for right now. So it's going to take in a bin string. And if you remember, the idea here is that if, for example, I had the string 1011, this is the ones place, the 2s, the 4s, the 8s. So as I go through here, I want to get each character and I want to turn it into its equivalent numeric, right? So we'll write this for binary first, and we'll kind of build it up. Because with binary, we know it's either a 0 or it's a 1. And as we do the math here, this guy is a 1 times, this is the 1s, 2s, 4s, 8s place. So 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. So we notice here that we only ever have to do anything when we're dealing with a 1. If we have a 0, 0 times anything doesn't impact the sum. So we only care if the current thing we're looking at is a 1. So we want to start at the end of our string, work towards the beginning of our string. So we're going to write a loop that's going to start at the end and work towards the beginning. So let's make sure we get that part going first. So we're going to break our problem up into smaller parts, okay? So we'll start off by saying, okay, I want to have a loop that's going to go through my bin string from the end towards the beginning. And for right now, why don't we just print out each of those bits? So we'll have our for loop. So for I in range, and the last legal bucket in bin string is the length of bin string. the length of bin string minus 1. That's the last legal bucket in there. We want to count backwards until we get to -1, not including -1. And by counting backwards, that means we're going to be stepping by -1, stepping backwards. So like 4 to 3 to 2 to 1 to 0, including 0. All right, so this for loop will take I on a journey from the last bucket of bin string to the first bucket of bin string. So if I just print out I, we're going to see that I is just a number. So I'll just go ahead and call binary to decimal, and I'll pass it 1011, for example. So this guy has 4 buckets. This is bucket 3, 2, 1, 0. So I each time is going to print out, the first time it'll print out a 3, which is the last legal bucket in bin string. Then it'll count down by 1, it'll print out a 2, then a 1, then a 0. So there's our 3, our 2, our 1, our 0. So all this for loop does is takes I on a journey. Now we get to decide how to use I. So I can say, well, instead of the number, I want to actually get bin string at position I. This will give me each of those individual bits. So this will give me a 1, then a 1, then a 0, then a 1. I'm accessing those individual bits. So now we're using that value of I to do something with it. All right, so now we want to ask some questions about the current character that we're looking at. So we want to ask a question. We're going to say, if the current thing we're looking at is equal to a 1, we want to do something. And what do we want to do? Well, we want to add something to a running total. So we need to remember a couple of things here, right? So we're going to have a running total. Maybe we call that guy sum. And we'll start our sum off at nothing, 0. And then we also are going to have a current place. So we start off at the 1's place, and the 2's, and the 4's, and the 8's, and the 16, so on and so forth. So we'll call this place, and place always starts off at the 1 place. So if I'm currently looking at a 1, I want to take my sum, and I want to add to it whatever the current place is. Because 1 times place is place. Correct? Now, if I'm not looking at a 1, that means it's a 0. No problem. 0 times place will be 0. I don't need to add anything to my sum. But regardless, I do want to make sure that place will be equal to place times 2 the next time through. So we go from the 1's place, times 2 is the 2's place, times 2 is the 4's place, times 2 is the 8's place. So every single time through this loop, regardless of whether we get inside this if statement, we will execute this one line. And we only add something to our sum if we're looking at a 1. Make sense? Then in the end, we'll go ahead and return the sum. So what will the output of this program be right now? Good. You think 7? Yeah. Okay. Yep. So it's nothing. Why is it nothing? What does that guy do? Oh, does it? What does it do? Read it. This calls a function, right? This is how we call a function. And you've told me that you believe that will boil down to a 7. What am I doing with that 7? Nothing. I don't see it on the screen. I'm not storing it anywhere. I'm not putting it in a variable. I'm calling the function. It's giving me a 7, and I'm doing nothing with it. If I want to see the answer from that, I can print it directly like that. And that'll get me my, actually, it is 11, isn't it? 1's, 2's, 4's, 8's. So 8 plus 2 plus 1 is 11. Okay, so I'm now printing it directly. So I got my 11 here, but I can't use it again. I could also store it in a variable. Maybe I call it answer is equal to whatever that guy returns, and I can choose to print answer. And then I can do something else with answer later on. I can use it for something else or whatever.
If we were visited by the same third race, we too could have access to all kinds of abilities.
My audiobook just started randomly playing. Well, that's the anime guys on Zoom. The cool kids will listen to audiobooks. Actually, I've tried to get into anime a bunch of times, but I keep falling asleep during them.
No, it's a good one. It's not really an anime. It's kind of like the good step to anime. It's called Avatar: The Last Airbender.
Yeah. I've saw the movie too.
The movie was trash.
Yeah, I get it, but I probably liked that better.
Oh, really?
Probably just because of the special effects and stuff like that.
Did you know the storyline?
Nah, not really. I mean, I sort of, kind of, maybe a little bit, but I never took it seriously enough.
Literally condensed to like over 100 episodes.
That's how all movies are.
Huh?
That's how all movies are.
Yeah, but that one was kind of ridiculous for most of them. Like they should at least have like 3 movies.
They probably should have for the money grab.
Yeah. So many people are so disappointed, and now they're doing another movie pretty soon actually.
Oh, so they'll still do the money grab. It'll make sense. All right, so in this case, I'm calling it, getting an answer, storing that answer somewhere, and then I'm choosing to print it if I want to see it. All right, that makes sense? This goes back to this thing we were talking about last class about always making sure we think about what does each line actually accomplish? What will this boil down to? And what are we doing with the value it boils down to? Okay, so this makes pretty good sense for binary to decimal. Now, if we want to upgrade this, let's say I want to go binary to octal. And we'll update our variable name to be an oct string, just since that's more appropriate. And actually, sorry, this is octal to decimal. All right, we're still going to have a sum. We're still going to keep track of our place. We're still going to go from the end of our string towards the beginning of the string. But now we can't just ask the question if it's a 1, add our place. Because if it's a 2, we want to add 2 times our place. If it's a 3, we want to add 3 times our place. If it's a 4, we want to add 4 times our place, all the way up to a 7, right? The legal octets in an octal number is 0 through 7. Now, 0 times place will still always be a 0, so we don't care about the 0 so much. But we don't just have this single binary if statement anymore, where if it's a 1, we care, if it's not, we don't. Now we have 6 values we care about. Well, 7 values we care about and 1 that we don't, right? So we are going to be interested in this current. I'm just going to store it here. We're interested in this current value. Now, I can print out that value, and we know we'll get the things that are coming out of that guy. So if I go octal to decimal, and I choose this guy to be 127, let's say, what will the output of this program be? So all programs begin and end with main. We start at the end of our list. So what's the first thing it'll print? 7, then a 2, then a 1. What's going to print right here? What is answer equal to? Answer is equal to whatever this boils down to. What does that guy boil down to? Do I return anything in here? Nope. So it'll boil down to none. So I should get 7, 2, 1, none. So a function that doesn't return a value will have a value, will boil down to nothing, which Python refers to as none. I'm storing none inside of answer, and I'm printing out that value. So what this guy does right now is he walks my string backwards, printing out the values of this in reverse, and then ultimately printing out what the function boiled down to, which is none. But now if I'm going to do math with these guys, because these guys are currently characters inside of a string, right? So if I go and I say I want to add something to this, if I just say I'm going to add 1, it's going to scream at me right now. It's going to say, hey, you can't use this plus sign to concatenate onto a string with an int. So I can just fake it for a moment and say I'm going to concatenate on a 1, and then I'll get 7, 1, 2, 1, 1, 1. So it's clearly showing us that this guy right here is a character type, not a number type. If I want to do math with it, I need to get it as a number type. So how can I turn a character type into a number type? Good. Yeah, so I have a function called int. So that will give me that guy as a number type. So now when I add 1, I'm getting 7 plus 1 is 8. 2 plus 1 is 3. 1 plus 1 is 2. So now I'm doing math with those guys. So this gives me the numeric version of the character that I'm currently looking at. So what do I want to do with that numeric version? Well, I want to say, I want to take my sum, I want to add to it the numeric version of the current value I'm looking at times place. And then I'll say place is equal to place times 8, since I'm dealing with octal. So place would be the 1's place, the 8's place, the 64's place, so on and so forth. Each time through, I'll take whatever character I'm currently looking at, whatever octet I'm currently looking at. I'll convert it from a string type into a numeric type that I can then do math with. Then I'll multiply it by place, giving me the product, right? Then I'll add it to my sum. And then each time through, I'll increase place by multiplying it by 8. Now in this particular case, I'm dealing with zeros, right? Sometimes this might be a 0. And 0 times place is going to be what? 0. 0 times anything is 0. So I'll just add 0 to sum. A little bit of a waste of time, but no big deal. Okay, but I don't have to have 30 if statements, or in this case, 7 if statements. I don't have to say, if it's a 7, do 7 times place. If it's a 6, do 6 times place. It's a 5, do 5 times place. And then just skip the 0. Instead, I could just say, look, whatever the value is, multiply it by place. If it happens to be a 0, so be it. 0 times place will be 0. I'll add that to my sum, and everything's fine. All right. So now my answer should be in sum. So I'll go ahead and return sum here. And this should give me 127 in decimal, which is an 87. So very similar to what we had up here, except up here we chose to just ask a single question. If it's a 1, I'm going to use the value. If it's not, it must be a 0, I won't. Down here we say, you know what, there's 7 different values this can be that I care about. So rather than ask a bunch of questions about it, I'll just say, give me the numeric version of the value I'm looking at and multiply that by place and add it to my running total. Each time through, increment place by, well, multiply place by 8.
What do you multiply by 8?
Because if we're dealing with octal, so if I go back here, if we have the, so in binary, this is the 1's place, times 2 is the 4's place, times 2 is the 8's place. I'm sorry, 1's place, times 2 is the 2's place, times 2 is the 4's place, times 2 is the 8's place. If this was octal, which is base 8, this is the 1's, this is the 1's place, times 8 is the 8's place, times 8 is the 64's place. So if I was converting from octal to decimal, when I walk from the end towards the beginning, because I'm dealing with base 8, I multiply by 8 each time. If this was decimal, 245, this is the 1's place, times 10 is the 10's place, times 10 is the 100's place, because it's base 10. Make sense? So that's our pattern for that. So for a 127 here, I'll put it after this just so our 127 in octal this will be a 7 times 1 plus a 2 times 8 plus a 1 times 64. And that is an 87, which is the same answer we got here from our output.
How do you know which one multiply by what?
What do you mean?
Like, why'd you do 1 times 7 and then 1 times 6?
Okay, because 7 is in the ones place.
Yeah.
So I say 7 times the place it's in, which is the ones place, plus 2 times the place it's in, which is the eights place, plus 1 times the place it's in, which is the 64's place. And then if I had, 254 in decimal, for example, this would be 4 times 1 plus 5 times 10 plus 2 times 100, which is going to give us 254. So there's our 254. So kind of a waste of time converting a decimal number into a decimal number, but the same pattern exists. This 4, we have 4 1s, we have 5 10s, and we have 2 100s. So 2 times 100 is 200, plus 50 plus 4 is 254. Okay, so it's the identical pattern no matter what we're doing. So if we go back over here and we want to write our waste of time function, it's actually not completely a waste of time because this will let us convert the decimal version of a string into the integer version of that string, but we already have a function called int that does that for us. But just to play the game, decimal to decimal, this guy will take in a, we'll call it a decimal string, name our variable something reasonable, decimal string, decimal string. The only thing that will change here is instead of multiplying place by 8, we'll multiply place by 10. So now we can call decimal to decimal on 127, and this should give us a 127. Converting the string version of decimal into a string version of a decimal number into its integer version of a decimal number. Because now this guy's a number, so I can add 1 to it. I'll get a 128. You can do math with it. All right, so that pretty much gets us up to right before the homework assignment. So this kind of gives us that pattern, right? We've evolved from it, that binary where it can just be 0 and 1 to all of a sudden now we have a whole bunch of different values it could possibly be. And I'll post the code on Slack at the end. But now we have our little curveball. So if we go ahead and we say, well, let's define hex to decimal. Actually, I'm just going to copy it and then we'll update it. So we'll call this guy hex to decimal. He's going to take in a hex string. There's my hex string. There's my hex string. And instead of multiplying by 8, I'll multiply by 16 because we're dealing with base 16 for hexadecimal, right? Now, all of this is the same exact pattern. But what are the legal hextets in a hexadecimal value? What are our hexadecimal values made up of? They're made up of 0 to 9, and then what? Yeah, A through F, right? First 6 letters. All right, so then A through F. So that means if I try to get the integer version of an A, come down here, and get that to come off the, oh, here, we'll just do this. I'll say int A. We see it's not very happy with us, right? We know that an A actually represents a 10. right? But Python's not going to be so happy about that. It'll convert the decimal, it'll convert, if I say int, the integer 9 as a string, it'll convert that to a 9. It's cool with the 0 to 9. But as soon as this line hits, and I happen to give it an eighth, B, C, D, E, F, whatever, and for larger bases, all the way through the alphabet, as soon as I hit that, Python's not going to be happy. So I can't just rely on this line working. Now, as it is right now, if I say, well, let's call hex to decimal on this guy, is this a legal hexadecimal number? Does it only contain values between 0 and 9 and A through F? Yeah, it's legal. That is a legal hexadecimal number. It's not an overly interesting hexadecimal number, but it's a legal one. So as of right now, my code will work for this guy because I don't have any of those weird letters to convert, right? So if I run this, I'll say, that's 295 in decimal. So if you have the hexadecimal value 127, that's the decimal value 295. The second I throw something crazy in here, like a B, it's gonna scream at me because the last time through this loop, it tried to convert that B into a number and it couldn't do it. So I need to have an alternate way of getting the numeric version of my values. We looked at this last class. So what we can have is we can have a string maybe called hextats and have this guy filled up with all of the hexadecimal values, or all the hextats. So the 0 is at bucket 0, the 1's at bucket 1, the 5's at bucket 5, the A is at bucket 10, the B is at bucket 11, so on and so forth. So now instead of converting this guy, what I'll do is I will use my find function. So I'll say hextats.find, and I'm looking for the character I'm currently looking at. If it happens to be a 0, it found it at bucket 0. If it happens to be a 7, it found it at bucket 7. If it happens to be an A, it found it at position 10. Now remind me, what does find return if we do not find a value? Go ahead. -1, -1. If we don't find it, it gives us a -1. That's an important thing. Doesn't help us here since we know we'll find it. If we assume that somebody's going to pass in a legal hexadecimal value, we know we're going to find the thing we're looking for. But in other uses for this tool find, it might be useful to say, hey, is the thing we're looking for, did I find it anywhere? If I didn't, that is, if it returned a -1, maybe I want to do something special, something like that. So we can use find to look for stuff. All right, so in this, go ahead.
Is there a difference between, or what is the difference between .index and .find?
.index, oh, there must be a .index of or a .index. I don't know. I don't know if they perform differently. They might do the same thing. Yeah. Yeah, it's just a function that's built in there. I mean, in Java, there's a function called index of, which is what I would use instead of find. So as far as I've seen so far, find works just like index of. So I would maybe assume that they're the same, but I'm not sure if one returns a different value or maybe find. Actually, here I can make a pretty good guess at this. I'm going to go ahead and, well, here, let me just run this real quick. Get this working, 299. We know what to expect with our BAD, right? We should get 2989. All right, so this guy now converts hex to decimal because we changed the way we converted, we mapped from our hextet to a numerical value that we can multiply with. Now, with that being said, if I create a list, and this is a 1, 2, 3, 4, and then I print out list.find a 2. Yep, doesn't work on lists, only works on strings. I would have actually predicted it was the opposite. Yeah, index does. So index works on any collection. Find works on strings. which is a little misleading because I would have actually expected index to, since other languages have an index of that is part of the string class, usually it operates on strings. But now I'm guessing, you said it did work on strings, so index works on all collection types, find only works on strings, something along those lines. But again, you want to think about it like, what tool do you have available to you? So for this assignment, I would have presumed that you would have said, okay, I need to solve. I'm always going to give you the tools that you'll need to solve the problem. So for this particular assignment, you would have looked in your little toolbox that you know doesn't contain every tool that exists, right? And you would have seen, okay, I have find, and we talked about this last class as well, and you would have tried to solve it with that. You know, because you could always Google and say, well, how do I search through a string for something else? But you already had a tool that did it. So you kind of wasted your money at Home Depot buying something you already had, that type of thing. All right, so this is hex to decimal. So now to complete the homework assignment, we'll evolve this one more time, and we're going to write base to decimal. Okay, and this guy will take in, let's just call it a base string. And then it's also going to take in a radix or a base, something like that. So I do need to complete my alphabet here. All right, so there's all of the possible values we can use to represent base 1 through base 36. Okay. So we'll go through every character by base string each time through. Instead of calling this hextets, I don't know what we'd call that. Mappings? Yeah, let's call it mappings. So we'll map from wherever we find this guy in this collection to give us a numeric value we can then multiply by. And then instead of multiplying by 16, we'll multiply by radix. All right, so same identical pattern, but now this will work on any base between base 1 and base 36. So if I want to call base to decimal on BAD, I need to advertise this guy's currently in base 16. And then it'll convert it for me. But if I say, hey, actually it's in base 17, I get a different value. Is this a legal base 17 number? Sure. What if I say base 36? Is this a legal base 36 number? Is it made up of 0 through 9s and A through Z's? Sure. So in base 36, this guy is that decimal number, 14,629. All right, makes some sense? So ultimately, this was the solution to the homework assignment, or a solution to the homework assignment. I suppose you can go crazy and have 26 if statements. If it's an A, treat it as a 10. If it's a B, treat it as 11. If it's a C, treat it as a 12, so on and so forth. But this would have been a better way of depicting that. Go ahead.
How do you come up with like the sum equals 0 and place equals 1 again?
Well, we're adding up a whole bunch of stuff. So whenever we're summing some stuff, we're going to start off with nothing and add to it. And then for place, the far right element here is always the ones place. Whether we're dealing with base 16, base 2, base 10, it's the ones place. All right. Other questions about this?
Oh, I got a question.
Sure.
I know you already went over this, but why don't we put the if underscore underscore main underscore equals main?
This guy? Yeah, so that's what we looked at last time with when we were dealing with variable scope. So I have this idea that, well, I've advertised this idea that all programs begin and end with main. And this is evidence that there is a such thing as main in Python. There's this like specially reserved variable in Python called underscore underscore name underscore underscore. So when this Python program runs, before we started doing this format, we just put everything out there in the middle of the global scope. So anything that was a function was an untapped resource. Anything we wrote outside of that, it would try to execute. What that would then let us do is it would allow us to have variables that were accessible inside of our other functions because they were part of that global scope. And our picture here probably depicts that maybe a little bit better. I draw this guy right here. So our global scope is what I have here in yellowish orange or whatever. Is that orange? Whatever that color is. So before, any variables or any logic we put lived in that global scope, and then our functions lived by themselves, but they would have access to all those values that live in that global scope. Realistically, that's not how good programming practice typically works. So what we've done here is we've said, you know, we have a function now called main. And now, as it stands right now, with our current code, none of these things actually exist in the global scope. We come back here, my global scope holds a function called main, it holds a function called baseToDecimal, all these other functions, doesn't hold any variables. So that means things that are defined inside of main, like for example, this variable answer is not accessible here, is not accessible here. If I want those to have, those other things to have access to those, I'd have to pass it along. So this is Python syntax for when a program first runs, it has a variable that says what function is currently running. And there's this thing called underscore underscore main underscore underscore, which is just a Python thing that says when my program starts, since all programs begin and end with main, what do I want to do? Well, what I want to do here is I want to artificially call my function I wrote here called main. I named it main, but I could have called this woot if I wanted to. If I want to call this woot, I just have to call it woot here, and it'll still work. But this is giving me a hard-coded entry point into my program where everything begins and ends right here, rather than having things kind of strewn about inside of the global scope. Does that make a little more sense?
Yeah.
But the specialty thing here is this is just special Python syntax for this variable called name that we don't typically use, and one of its potential values, which is underscore underscore main. We would actually find if I omitted this, it would still work. Because now this one call is sitting there inside of the global scope. So it's the first line of executable code it will hit. So it'll still run. It just happens to hit that line first. Where in this case, if I put it inside of here, and I don't know, I'll just make up a variable that doesn't exist. I'm pretty positive underscore underscore woot underscore underscore is not part of Python. So now my program won't actually do anything because the variable name does not hold this value. So this is evidence that when I said that all programs begin and end with main, Python plays by those same rules. Its main is called underscore underscore main underscore underscore. So I'm saying if it's trying to access main, what do I want to do? Go ahead and call my main function here. I could also just put this code directly under here if I wanted to. And say, this is the stuff that should happen when I'm executing main. I don't actually have to have a function like this to do it. I could do it inside of an if statement.
So that way it only does stuff with the baseToDecimal one, right?
Yeah, well, correct, because all these are just abilities. You know, I just happen to not be calling binary to decimal right now.
Okay.
It's an untapped resource. It's a function. I wrote it. I can use it, but I'm not using it yet. We have this toolbox with a bunch of stuff in it, and I'm only using a couple of the things from that, but the other ones are accessible to me. All right, so the way I kind of like to write this, though, is I like to compartmentalize stuff inside of functions. So I'm just going to have this little stupid syntax here that says, look, if Python tried to call main, let's just go ahead and call my main function that I wrote. I happen to name main for traditional reasons, because all programs begin and end with main.
What's the name underscore part for?
This is a built-in Python thing. So when Python first runs, we will have there's a variable that exists called underscore name that will be equal to some string. And it's what is the name of the function I'm trying to call. And in this case, it'll be main. It's something that Python does automatically, not something we have control over, and realistically, not something you necessarily use that often. All right, so go ahead.
As the for loop is going on, how does it know to take the radix or place times radix? I don't understand. It's from 16 to 256 to 4096 like it should be. But I'm not understanding. Like I wouldn't know how to write that.
Right there. Isn't that what you're asking?
Yeah, but I don't get how.
Well, what does place start off as?
1.
Okay, here, let's look at octal. That way we have a hard-coded value in here. So place starts off at 1. So now I'm going to set place equal to, I'm updating the value of place,
Right.
equal to the current value of place, which is what? What's the current value of place? It started off as 1 times 8. 8 times 1 is 8. So now place is equal to 8.
I thought it would have changed the value of place at that point.
It is. It does. It changes it right here. So after this, so this says set place equal to a new value. What value? Whatever place is currently equal to, which is 1, times 8, which is 8. So after this line executes, place is now equal to 8.
Sorry, that's what messed me up.
Next time through, set place equal to its current value, which is 8, times 8, which is 64. So now place is 64. Next time through, it'll be times 8 again, so on and so forth. All right, so let me put this on Slack so you have this code. What do we call it? Base-to-decimal. Okay. All right, so we're going to talk about a concept here of pass by value versus pass by reference. I've probably mentioned it in passing at some point, but we're going to dig into it a little bit. We have this idea of something called a pointer. I probably have it in here somewhere. Pointer. So a pointer, this is a variable type. So at this point, we've seen lots of different variable types, right? We've worked with integers, we've worked with strings, we've worked with chars. So we have this variable type called a pointer. And a pointer is a variable type who's capable of holding a memory address. All right. Now, this is a really important concept that's often a difficult concept for beginning programmers to wrap their mind around. Again, this comes down to the idea that hexadecimal values are intimidating. So I mentioned, I don't know if it was last class or the class before, that in computers, all of our memory addresses are all in one big long road. We all live on one street. Okay, where in real life, our addresses in real life are much more complex, right? You have your 1, 2, 3 Adams Street, right? In a town with a zip code and all these other things. We have lots of parts to our addresses in real life that are far more complex than addresses work inside of computers. But because we've been used to using those addresses our entire life, probably in kindergarten, you had to memorize your home address or something. Whenever they made you memorize those things, we've been dealing with these things for years and years and years and years. So the human version of addresses doesn't really scare us. Computers' addresses are actually significantly simpler. We have one street on the entire planet. A big, long street. and all the houses on that one street. I'm house number 2, I'm house number 3, I'm house number 17,241. You know, you're just one of the houses in this line. Now that sounds pretty easy. Sounds like kind of a tiresome walk for the mailman if if everybody's on one street, but you know, you kind of get the point. From a conceiving of how this kind of thing works perspective, having everybody living on one street is pretty easy, right? We get intimidated because the way computers represent memory addresses is with a hexadecimal value. Why? Something we probably have seen as we've gone through this. Notice that as I increased the base here, the decimal value got bigger. So BAD in base 36 is actually an equivalent representation of 14,629. So even if we just look at this simply, this took 5 digits to represent. This only took 3 characters. So I was able to represent a very large decimal value that we're comfortable with in a much smaller footprint with a bigger base. So if I go back to, you know, base 16, which is the one we typically use, I get 2989, so that's 4 digits I was able to represent as 3, as an example. So the idea here is by using base 16 instead of base 10, I can represent big numbers in a smaller footprint. That's why computers choose a larger base to represent our memory addresses. Why did they choose base 16? Because we have that shortcut thing with base 16 where we can create the groupings of 4 to convert between binary and base 16 very easily. Similarly, we like octal because we can create groupings of 3. All right, so base 16 happens to be compatible with digital logic, happens to be able to conveniently move between it and binary. And at the same time, it lets us more compactly represent addresses because those numbers start getting really, 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 really big, right? Because when we think about our computer's memory, how much memory do we have inside of our computer? All right, so how much memory is in our computers? 8 gigs, 16 gigs? Let's go 16 gigabytes. So kind of a pretty decent modern computer has 16 gigabytes of memory. There's computers that have more, computers that have less, but 16 would be considered a pretty reasonable computer today. So we have 16 gigabytes of RAM in a good modern computer. All right. Now, most of our operating systems today are 64-bit operating systems. We've heard that before. It's a 32-bit operating system. It's a 64-bit operating system. Maybe you've heard it for years about your video game consoles. It's a 32-bit console. It's a 64-bit console, something like that. So that idea of it being 32-bit or 64-bit, that says potentially many things about the operating system. But one of the things it very likely says, because an operating system has a whole bunch of subcomponents that are part of it. You'll learn about this in the OS class. But one of them is memory management. You know, one of them is putting all those houses on that one street, and how do I reference one house as being different than another house being different than another house? So in a 64-bit operating system, typically we would use 64-bit addresses. So that means that I can have 2 to the 64th power number of houses maximum in my with 16 gigabytes of RAM. So if I have a 64-bit operating system and I have 16 gigabytes of RAM, we throw out that we might use some of that RAM for some other things. Theoretically, we have this many plots of land to build a house on. Make sense? Okay, that's the number of memory addresses we can have. Now, with that in mind, this is a pretty big number in decimal, right? We can represent this number in significantly smaller fashion if we convert it to hexadecimal. It'll still be scary looking. You have a bunch of A's through F's in there and some numbers and things like that. But ultimately, we can just look at this and say, you know what? With 16 gigabytes of RAM and a 64-bit operating system, I have a whole lot of houses that live on this one street. And I need to have a big enough number, a big enough value to link them all if I'm going to have 16 gigs of memory. So for instance, if I have 16 gigabytes of memory and I only have an 8-bit operating system, let's say, that's 2 to the 8th, that's 256. So that means I can actually only have 256 unique things in memory at once, which isn't that much. Even if I have 16 gigs of RAM, I can only have 256 unique stuff in memory. So each one of them potentially could be a gigantic mansion, right? To fill up that neighborhood, the 16 gigabyte neighborhood, but I can't have that many of them because I'm only representing them using an 8-bit memory address. With a 64-bit memory address, I can have that many unique things stored in memory, maximum, which we could say, you know, for right now, that's probably safe. Realistically, 32-bit is probably enough for memory management for right now. 4.2 billion unique things in memory is probably enough. Okay, so if we took our 16 gigs and we divided it by this guy, that means the average size, you know, we can think of the average house size on our computer could be this in gigabytes. So if I multiply that by 1024, that's megabytes, times 1024, that's kilobytes, times 1024 is bytes. So that means if all the houses in our computer's memory were the same size, which that's not how it probably works, right? You're going to have some tiny things stored in memory, and then you're going to have some giant things stored in memory. But if all of them were the same size, that means I can store 4 bytes of information. You know, that's the size of the house. 4-bedroom house. 4-bedroom house, and you can have 4.2 billion of them. That's what will fit in 16 gigabytes of memory. All right. But our computer's memory is meant to be able to store different size things. Sometimes we're going to want to store a giant image that is 4K that takes up a whole bunch of space, and sometimes we're going to want to store a character that only takes up 16 bits, 2 bytes. Make sense? All right, but punchline is that depending on the number of bits the operating system is, specifically the memory manager of the operating system, that's going to tell us how many houses can live on our computer. Houses being unique pieces of data that we're going to store in memory. So with that in mind, we have a data type called a pointer. It has the ability to hold a memory address. Now, in Python, and we'll see this when we get a little bit farther in, when we get into objects here pretty soon, we'll actually see some memory addresses printed out. But we can tell that memory addresses exist in Python because of how things are passed, and we'll see this here in a second. So right now, we're going to say we have this fictional type called the pointer. And all a pointer does is it holds a memory address, which is effectively a number that links to one of those spaces in memory. Or reason it's called a pointer, it's a number that points to one of those spaces in memory. All right, so at the high level, does that make some sense? We have a data type that holds a memory address. All right, now with that in mind, we want to think about how values can be passed. And we're going to look at this through some examples. I'm going to come back over here. I'm going to go ahead and gut our code from today. I already put it up on Slack. All right, so I'm going to write a couple of functions here. I'm going to say def change num. I'm going to have this guy take it a number. And we'll say print a num. Then we'll say a num is equal to 5. Then we'll print a num again. And I'll create a variable here called sum num. And I'll start this off at 13. And I'll go ahead and print out sum num. Then I'll call change num, passing it sum num. and then I'll print out some num again. So if we walk through this code, we want to think about what do we expect. So all programs begin and end with main. So this line right here defines a variable called sumNum and puts a 13 in there initially, right? So when I print out the current value of sumNum, what's going to print out? 13. All right. Now I'm calling my function called changeNum, and I'm passing sumNum in as a parameter. So sumNum is going to get passed in, and internally inside of changeNum, it's referred to as anum. This is what I call the variable. So now I'm going to print out the value of anum, which is what? 13. But then I'm going to change anum to 5. And then I print out anum. What's it going to print out? A 5. So now this function ends, right? So now I'm back to this line right here. What's the current value of sumNum? Okay, so potentially it could be 5 because I changed it in here. Or it could still be 13. In this case, it's still going to be 13. So let's prove that. Run it. We see that we have 13, 13 for the first 2 times. So it printed out here and it printed out here. Then I changed it. It printed out here, so it became a 5. But then when I came back out here and I printed out sumNum, it reverted back to its old value of 13. Okay? What we would say here is that numbers, so the type of value this is a number, it's a numeric value, are passed by value, not by the alternative is reference or by address. These guys are passed by value. So what do I mean by that? So let's say you come up to me and you ask me for a quarter. And I have 5 quarters in my pocket. Actually, let's say I'm a magician. I have 1 quarter in my pocket, but I can make a duplicate of it. That's really what's happening, right? I'm giving you a copy of the quarter, okay? So now you run off and you do something. Let's say you melt the quarter, like pyro, like playing with the fire or whatever. So you go and melt the quarter. Is that going to have any impact on the quarter I still have in my pocket? No, because I gave you a copy of it. Make sense? That's what's happening with our primitive types in Python. If I pass a string, or I pass a character, or I pass a int. Strings are a little bit wishy-washy because they're actually object types, but they behave like primitive types. That's why I throw it into that category. All right, so any of our simple types in Python are passed by value, which means when I passed in sumNum here, it got a copy of that value, not a direct link to it. So this boiled down to a 13. A 13 came in here into anum. And as far as this is concerned, anum lived and died inside of this function. Make sense? So that's called pass by value. Okay, that's called pass by value. Now, we're going to have a function here called changeList. And what we're going to do is we're going to print out the list. And then we're going to say a list at bucket 0 is equal to, I don't know, we'll change it to a 5. Then we'll print out a list. And then what I'll do, I'll just have a second section here since I'll post this up on Slack as well. So I'll create a list here called my list, and this is going to be a 1, a 2, a 3. I'll go ahead and print out my list, which will print out a 1, a 2, a 3. Then I'll call changeList, passing it my list. And then I'll print out my list again. Okay, so we walk through this. This effectively does the same thing we just did previously, but we're going to see the result is different. So my list is the list 1, 2, 3. I'll go ahead and print that out. We expect it to give us the list 1, 2, 3. Then we call changeList, passing in my list. And here we refer to it as a variable called a list. They're synonyms. We'll print out a list, which will print out 1, 2, 3. Then we're going to modify bucket 0 of that list. And we're going to change this 1 to a 5. We'll print it out again and we'll see a 5, 2, 3. Then when this function ends, we come back out and we print my list again. The question is, will it have reverted back to its original value like we just saw before in the previous example? Or will this change of taking bucket 0 and making it a 5, will that be permanent? In this case, it will be permanent. We'll see that it is now permanently 5. That is to say, it had side effect. Why is that? It's because when I passed this value here, when I passed this list right here, I passed it by address. So when you were making changes in here, you were changing the original thing, okay? So the real life example would be this. Let's say that I handed you a piece of paper that had the address of my house, okay? And you go to, I'm still the magician, right? So I have a piece of paper that has the address of my house written on it. You walk up, I make a copy of that address. Still says the same thing, right? Still has the same address on it. I hand you the address, and you go to my house and you spray paint my garage door. When I get home, am I going to be surprised? You went to my actual house, right? We both had a piece of paper that both had the same address on it. It's two physical things, right? I gave you a copy of my piece of paper that had the address. But at the end of the day, when you went to make modifications to what was at that address, you went to the same place that I'm going home to tonight, right? So that has side effect. When things are passed by address or passed by reference, sometimes it's called, what you're doing is you're giving them a pointer to where they can find the value in memory. I'm giving you the pointer where you can find my house in Grafton. So when you go there and you make changes to my house, that's not a copy of my house, it's the single house. Make sense? Go ahead.
Is the bucket then, like the bucket 0, the actual passing of the address into the list?
This is the actual address being passed. This is saying I want to access bucket 0 of the thing at that address.
Okay, so the list itself, because a list is why it's an address, or why?
Yeah, lists are passed by address. So this kind of are simple data types. If we want to kind of keep the concept fairly simple at this point, are simple data types like integers and chars and strings. They are passed by, I know strings and lists are very similar, but let's for right now just allow me to say that strings are simple because they're used so often. Python treats them as our simple variable types, even though they're a little bit more capable. So our simple variable types, they are passed by value. Our more complex data types are passed by address. And this makes sense in real life. For instance, if I walked up to you and I asked for a quarter, assuming you were generous and you had an extra quarter, or you were the magician guy that can just make quarters, which, would that be a good superpower? I mean, on one hand, you could make infinite money, but you're making it 1 quarter at a time. It'd be like really inconvenient to spend. There's this guy carrying out bags of quarters, counting them out at Wendy's. All right, so, but let's say we're the magician guy and you come up, you ask for a quarter, and I duplicate the quarter in my pocket. I hand you the quarter. That makes sense, right? Quarters are nice and light, not a big deal. Wouldn't you be kind of ticked off at me if I said, oh, I'll give you a quarter. Let me tell you when I last saw one. It's about 6 blocks down to the left. You know, I think I saw a quarter next to the drain. You know, like sending you on a wild goose chase to go find where a quarter was stored in memory. That wouldn't make a whole lot of sense, right? Because quarters are tiny. They're easy to hand off, right? But if, let's say that you're having a party at your house tonight and you're inviting social distancing and everything, you're inviting your buddy Mike to this party, you wouldn't hand me the house and tell me to open the door at 8, right? You would tell me where to find your house. You give me the address to the house because houses are heavy. Doesn't make any sense to hand somebody a whole house. Make some sense? So Remember, programming languages are attempting to allow us to solve problems in ways that are similar to how we solve problems in real life. So this is a truth right here as well. If I'm just giving you a number or a quarter, these are small, tiny little values, not a big deal. I can give you, in computing, we can be that magician where we can make a duplicate of the quarter, make a duplicate of the number, and I can hand you a copy of it and say, hey, have at it. It's all yours now. What I just gave you will have no impact on me, or no side effect, is what we typically would say. That makes sense in real life. It's a nice light value. It's not overly burdensome. I can just hand it off. But in real life, if you're giving, telling somebody wants to borrow your car, you don't hand them your car. You give them the keys and tell them where they can find it, right? It's parked out in J-Lot or something like that. All right. So in real life, these same things make sense. Python is saying, look, for our more complex data types like lists, like dictionaries, these guys are passed by address because they're heavy. I'm going to tell you where you can find that guy so we don't have multiple copies of these potentially big things floating all over the place. Where a small value like a number, no, you could have a situation where it's still potentially inefficient, where technically the memory address version of this would have been a little bit smaller than the value itself, maybe for like a really big number. But realistically, we are only wasting a little bit of memory there. There's no such thing in real life, even if you live in one of those nice little tiny homes. You've seen the TVs, the documentaries for the tiny houses, where they're like this little tiny, they're still too heavy to hand somebody, right? Yeah, you're not going to walk up and just hand somebody a tiny home. So houses are always too heavy. So we're going to say it would be very inefficient for me to walk around handing somebody a house. So we'll just always tell them where they can find it. Go ahead.
So by calling the change list function and then putting my list in it, it's gonna hold that location until it's done parsing or whatever.
What's really happening there, so if I draw a picture of this, so we have change list and we have main. So inside of main, we have, so here, I'll just say main here, and then I have another function called change list. And inside of main, what did I name my list? I called it my list. And inside of change list, I named it a list. And up here in memory, we have an actual list. 1, 2, 3. So when we first came into main and we created my list, it went ahead and it created a place in memory to store that list. And my list held the memory address, or it points to that place in memory. When main then made a call to change list, so inside of main, we had a call to change list, and we passed it my list like this. What happened then is a version of change list came in. We had a variable called a list that my list was being passed in for, but instead of it being a copy, a list pointed to the same place in memory. So these guys, they both point to the same exact location in memory. Think of this like my house in my example. If I tell you where I live and you run and spray paint my garage, when I get home, I'm going to see a spray painted garage. All right. So change list started, it printed out this guy, and then it changed the value here to 5. Printed it out again. But then when this guy died and this pointer went away, because it was a local variable that lived with change list, and now that function's dead, we come back to main. My list still points to the same place in memory. But what do we find in memory now? We find a modified value, because these variables were pointers to a place in memory. Yeah.
I might be asking if you've already thought about it, but how come when I run it again, it goes back as it?
Because we started the program again. When all programs begin and end with main. So when you run it again, we're defining a variable called my list. We're setting it equal to 1, 2, 3. It's potentially in a different place in memory, all that stuff.
But if I didn't run it again and I let it sit, is that still technically, like, would that 5 still be?
Oh, yeah.
in the system
Oh,
or
yeah.
memory?
Yeah, I mean, if we were, well, I mean, we saw it. It's still printing there.
Yeah.
But yeah, I mean, if our program was still running and we went on and did it again, yeah, that's there. For as long as our program runs.
So if I printed my list after I ran it, it should print 523.
Oh, if you're saying after you run it inside here, will it still be 523 out here from the real-time interpreter?
Yeah.
I don't know about that.
Just the whole time.
I'm guessing the answer is yes, because I think this interpreter, print my list. Yeah, it's the variable's not defined. So once your program ended, any of these things that were defined in there were gone. And that has more to do with just the interactive interpreter than something you need to memorize. Okay, so that's kind of the nature of pointers. That's what the slide is basically saying, is for variable passing, we have two different things that can happen. We have pass by value, which do not have side effect. Not having side effect means that any changes that happen in a function whose variables were passed in by value, any changes that occur in there will not be felt outside of that function. They do not have side effect. As opposed to pass by reference or passed by address, a pointer to that thing is passed. So any changes will have side effect because you're actually making manipulations to the actual place in memory. All right, that makes some sense? All right, so we're actually going to, for our homework, we're going to write a couple of different things here. So let's just see how bad these are. So this is a simple one. Yeah, so we're going to write these first three things here. So the first one, we're again practicing with functions, things like that. We're going to write a program that prompts the user for a temperature, and it displays to the screen whether they need a heavy coat, a light jacket, or no jacket. Heavy coats are worn when it's below 50. Light jackets are worn when it's below 67. Otherwise, no jackets required. All right, so just practice writing a program that asks some questions, things like that. So this one should be pretty quick and dirty, pretty easy to write. So then the next one, I give you a link to Fibonacci number sequence, which is, you know, each number is the sum of the previous two numbers. That's how Fibonacci works. You can read about it. So write a program that fills a list up with the first 1,000 numbers in the Fibonacci sequence. So make sure you test your output by printing some of the elements in your list to know how the logic is working. So now you're going to generate the Fibonacci sequence. Go ahead. No, I think Da Vinci came up with the Fibonacci sequence. Then the last one is dealing with prime numbers. So prime numbers are numbers that are only divisible by themselves and 1. So you're going to write a function named isPrime that takes a single parameter and returns true if it's a prime number and false otherwise. So make sure to test your function by calling it with various numbers. So like, for instance, a number 3 is a prime number. Number 4 is not, because number 4 is evenly divisible by 2. So not just itself and 1. It's divisible by 2 as well. Okay? So 3 different functions, 3 different, I would rate them as functions for your homework assignment. We'll solve those next time, and then we'll probably write a couple of these in class. And then we're moving on to Unit 4, which we're going to start dealing with classes, writing our own objects. Okay? Questions, comments, concerns, bribes? All right, I'll see everybody on Tuesday.